Welcome. Today is September 6th, 2009, and this is a special edition of the Mars Reconnaissance Orbiter HiRISE Photojournal. With this first image, it's a fan in the southern highlands crater. Many channels formed by water when the climate of the Mars was very different to that of today cut the ancient highlands of Mars. Water running through these channels picks up rocky debris and carries it or rolls it along the channel bed. Occasionally, these channels will empty into a crater or other low point in the terrain, and the water would drop the material it is transporting. So, this material can build up in large fan-shaped mounds at the end of the channel. This is similar to deltas that we see on the Nile Delta in Egypt. In this observation, this is likely what has happened. The fan-shaped mound, which appears bluish in this false color image, sits at the end of the short channel. Analysis of the spectroscopic data shows that the composition of this material indicates a history of interaction with liquid water. The full resolution version of this HiRISE image shows layering that indicates this material was dumped here in at least 3 separate episodes. Although they may once have been common, features like this are now rare. Scientists study them to try and understand how much liquid water affected the composition and appearance of Mars in its earlier history. In this next image, it shows several years ago, gullies carved into high slopes and the walls of impact craters like the ones pictured here were discovered. Scientists are excited to study these features because, on Earth, they usually form through the action of liquid water, long thought to be absent on the Martian surface. Whether gullies formed under today's cold, dry conditions is a major question that planetary scientists are trying to answer. The gullies pictured here are great examples of what a typical Martian gully looks like. You can see wide V-shaped channels running downhill from top to bottom where the material that carved the gully flowed. At the bottom of the channel as material empties out into a fan-shaped mound. Several gullies are visible here, and the fans from each gully overlap one another in complicated ways. At the top of the channels, large amphitheater-shaped alcoves are carved in the rocks. The material removed from these alcoves likely flowed downhill to the aprons through the gullies. Gullies at this site are especially interesting because scientists recently discovered examples at similar locations to still be active. Images separated by several years showed changes in the appearance of some of these gullies. Today, planetary scientists are using the HiRISE camera to examine gullies for ongoing change and investigate what that might mean for the occurrence of liquid water on the surface of Mars. Throughout this entire image in Aonia Terra, it is possible to make out regular polygonally shaped patterns. Here on Earth, wherever ice-rich permafrost occurs, soil which stays frozen throughout the year, the ground may crack and form similar patterns to those we see on Mars. Despite remaining below freezing, changes in seasons and ground temperature cause significant thermal contraction stress, enough so that the terrain fractures into a honeycomb network of subsurface cracks. Crisscross dark paths wind throughout this region. Dust devils, turbulent whirlwinds fueled by rising ground-warmed atmosphere, trek across the surface, stripping the ground of bright surface dust as they go. Comparable to miniature tornadoes, they efficiently transport surface materials on Mars. Left in their passing is the darker, coarse-grained soil underneath. In this image, the sun is low in the horizon. The shadows make it easier to see the scattered rocks and boulders. Sometimes these boulders occur in rings, the remnants of the ancient impacts whose crater has since eroded to the flat surface. The boulders are left behind, illustrating where the form of the crater once stood. The ground appears to have a linear pattern, somewhat easier to see viewing the entire image at once, extending from the bottom right to the top left of the image. The linear pattern of the light bedrock is especially evident in nighttime infrared images, where it appears as a series of bright streaks or rays. The pattern points directly back to the Hale crater. Another series of bright rays were formed during the formation of the Hale crater too, and extend almost to Valles Marineris, over 1,000 kilometers away. Unlike the rays, the pattern in this HiRISE images has relief, so it appears to be areas of bedrock, light areas that have been grooved or scoured in a uniform direction. Superimposed on this in the low-lying areas are dark areas that consist of small ridges trending in the opposite direction to the scoured bedrock. The dark areas are sand and dust, and the small ridges are aeolian bed forms. The suggestion that the pattern arises from the bedrock that has been scoured along a linear trend away from the Hale crater is interesting because an outward expanding blast of pulverized debris, a type of which is known as base surges, is thought to be one of the features associated with the formation of impact craters. This HiRISE image shows a close-up view of the terrain northeast of Ziller crater. In lower resolution images from the context camera, also on board the Mars Reconnaissance orbiter, this area looks quite rough. The reasons for this rough texture are difficult to determine. However, clues from the surrounding area help solve this mystery. Many large impact craters surrounding this image, but there are no volcanoes nearby, making it unlikely that the rough surface is from fresh, blocky lava flows. The high-resolution image shown here reveals a few fresh, irregularly shaped craters on top of this rough terrain. An irregular crater, approximately 600 meters in diameter, is visible just right of center, about a third of the way up from the bottom of the image. Its shapes suggest that it formed from a body that impacted the surface at a relatively low angle and slow speed. This makes it likely that it is the secondary crater, the crater that forms from debris blasted out of a nearby crater. The rough terrain here is therefore likely to be a mix of impact material and secondary craters from nearby impacts, such as the one that formed the nearby large crater Ziller. This dune fill in Anya Terra shows sand dunes with a variety of morphologies. These complex shapes often indicate that the dominating winds change direction, either over time or from one location to the next. Many of the dune fills in this region of Mars are banked up against topographic obstacles such as crater rims. The location of the dunes within impact craters gives an indication of the average regional winds, while details such as slip face orientations and superimposed ripples are controlled by the present-day local winds. The outlined dunes in this image appear as simple arc-shaped barctions formed by southerly winds. As the dunes migrated northwards, they encountered other dunes crowded against a confining scarp. Many of the barchans climbed up into the upwind slope of the next row of dunes. This migration is known by the avalanches that have occurred on the downwind slip face of the dunes. The collision of the dunes altered the morphology of the barchans to the star-shaped dunes with the multiple arms that look at a linear appearance as the horns were modified. There is also the presence of faint dark tracks from dust devils picked up a very thin veneer of dust on the dunes. The faintness of the tracks could be an indication that the dunes are actively saltating sand grains that clean much of the settled dust from the dunes.